Welcome to the Amplifier session, Capture Signals and Drive Precision Systems. My name is Gustavo Castro. I am a Senior Applications Engineer with Analog Devices in Wilmington, Massachusetts. Today we're going to talk about operational amplifiers, noise considerations, instrumentation amplifiers, ADC drivers, high common mode voltage applications, and amplifier design tools. We live in an analog world. In order for computers to interface to our analog world, we require analog to digital converters, digital to analog converters, sensors, and actuators. The devices that allows us to connect those sensors and actuators to our converters are the amplifiers, and those are in charge of the signal conditioning part. Amplifiers make a low-level, high source impedance signal into a high-level, low source impedance signal that converters can understand. Op-amps, power amplifiers, RF amplifiers, instrumentation amplifiers, all of those are examples of amplifiers. The most common device is the operational amplifier, and this is a three-terminal device that can amplify small signals that are present at its inputs. They're called operational because they can be configured to perform different operations or functions. These include positive amplification, inverting amplification, filtering, nonlinear transfer functions, etc. These find applications as fundamental building blocks for analog design. Sensor amplifiers and complex filters, as well as ADC driving. Key op-amp performance features include bandwidth and slew rate, which tell us how fast the amplifier is, offset voltage and current, which tells us some of the errors of the amplifier, and ultimately determines measurement accuracy, as well as noise, which limits how small of a signal can be amplified with good fidelity. Standard configurations are non-inverting, which are shown here at the top, as well as the inverting. The difference between these two is the relationship between the input and the output signal. You can see that in the non-inverting case, the output and the input have the same phase. In the inverting case, they have opposite phases. The op-amp error sources are listed in this slide. There's input impedance, input bias current, there's an output impedance, an offset current, and an offset voltage. These are just the most important ones, but will help us in explaining some of the sources that make an amplifier non-ideal. For example, an ideal non-inverting amplifier will simply amplify the input voltage by the relationship 1 plus R2 over R1. In reality, there needs to be a small differential voltage between its inputs, which is shown here as VID. If we express this equation at the bottom in a different way, as 1 over beta times Vin minus VID, we have the equation at the top. If we include all the differential errors included in that voltage, VID, then we have a slightly different transfer function for our output voltage. This one includes noise and other errors. Because the noise En gets multiplied by that term 1 over beta, we term this the noise gain. The noise gain is always the gain of the non-inverting input. So you can see that the noise gain of an op-amp can never be less than the signal gain. If we compare in all these three cases, the signal gain and the noise gain may not be the same, but the noise gain is always the gain of the non-inverting amplifier. The total noise calculation is shown on the slide at the bottom. So you can see that all the noise factors here in the amplifier are multiplied by gain, by the noise gain. And some of the resistor contributions are multiplied by the noise gain minus 1. sometimes we need to determine exactly what is the dominant source of the noise. As you can see from the previous slide, both the resistors, the source impedance, and the amplifier contribute to noise, and it is very important to understand which is the dominant source. In this example, the AD8675 is an operational amplifier with a voltage noise density of 3 nanovolts per Hz and a current noise density of 1 picoamp per Hz. The contribution from the amplifier voltage noise is dominant when the value of that source impedance is 0. However, when the value of the source impedance is something around 3 k ohms, the Johnson noise of the resistor dominates to give us a total of 7 nanovolts per Hz, as opposed to the expected 3. If we make the source impedance value 300 k ohms, the amplifier current noise is amplified by flowing through the resistor, and it becomes 300 nanovolts per Hz. Keep in mind that for this example, we have neglected the noise contribution from R1 and R2. In this situation, we would like to, if we have a large source impedance, we would like to make the amplifier, pick an amplifier with the lowest current noise possible. 1/f noise is another figure of merit for amplifiers and is usually dominant in DC applications. The position of the 1/f corner determines how much 1/f noise is present in any DC application. For instance, take the ADA4528. This is a zero drift amplifier that uses a special technique to reduce 1/f noise. As can be seen from this slide, the input referred noise is only 97 nanovolts peak to peak. Some of the key features of the ADA4528 is that it's very low offset and there's virtually no 1/f noise. As you can see, the 1/f noise is shifted to a higher frequency when it's easier to filter. This is why we like to use this type of amplifier for DC applications. This is an example of a precision weight scale design using the AD7791 and the ADA4528. This example has been optimized for DC measurements, and in this case we're showing the conditioning of a load cell. 4528 creates the differential gain that is then sampled by the AD7791. ADI amplifiers are based on process innovations. Advanced process technology such as bipolar, JFET, CMOS, iCMOS, iPolar, and LD20 enhanced CMOS allows us to create world-class amplifiers. Some of the enablers for those high-class amplifiers are design techniques, process technology, trim techniques, package technology, and test techniques. The resulting benefits are improved robustness, high-performance amplifiers, low noise, high precision in small plastic packages, higher precision, improves offset and TCVOS performance. Another example is the AD8597 and AD8599. These are 1 nanovolt per Hz ultra-low noise amplifiers with an ultra-low 1/f corner. This is very low noise at a very high precision. A current noise of 1.5 picoamp per Hz and a unity gain stable with a high output drive up to 50 milliamps. An example of this amplifier is shown in this slide, where it's optimized for an 18-bit circuit at 250 kilosamples per second sampling rate. The circuit node is CN0261 if you'd like to refer to it later. On the actuator side, we also have amplifiers examples such as this 20-bit linear low noise precision bipolar. This plus and minus 10 volt DC voltage source, which is shown in the circuit node CN0191, has a 1 ppm resolution and needs low noise from every component. It is important the amplifier choice for the buffer of a digital to analog converter. In this case, we're showing a digital to analog converter that has a very good linearity, well over under 1 LSB. Buffering the output of this digital to analog converter with a rail-to-rail input amplifier can create some linearity problems due to input crossover distortion. This is caused when the amplifier has two input stages. In this case, we're showing an N-type and a P-type input stage. And when the crossover point is reached, that means when one input stage is used and then we cross over to the other one to reach the other end, there is that small distortion that is shown on the bottom right of the screen. This can be solved with zero crossover amplifiers such as the ADA 4500. An internal charge pump biases the input stage so that it can reach the rails without having to have a second input stage that's going to create the crossover distortion. We can see that buffering the output of that digital to analog converter gives us the same INL and DNL as we had before. So what else can op-amps do? Op-amps can do virtually anything. Amplify, filter, level, shift, compare, and drive ADCs. The circuit design sometimes becomes difficult when the system is a little bit more complex and requires multiple amplifiers, multiple passives, or good matching between the passives. This is when specialty amplifiers can help. They are designed for specific signal types or specific functions. They sometimes include passives on chip that are well matched and then can deliver high CMRR and then also high precision. There are multiple integrated amplifier products. Some of them are listed here. We have current sense, difference amplifier, instrumentation amplifiers, variable gain amplifiers, RMS to DC converters, thermocouple amplifiers, and multipliers. We need to talk briefly about single-ended versus differential signals. Single-ended signals, we refer to signals that are measured referred to ground, and when signals are bipolar, plus and minus, negative supplies are required. In contrast, differential signals, both sides of the signal can float off ground. They can be anywhere. Signals are separated from ground and other signals, and command mode can be set for a single supply. To work with differential signals, we have the following amplifiers: instrumentation amplifiers, difference amplifiers, and differential amplifiers. These amplifiers typically take a differential input and amplify it. In the case of instrumentation amplifiers, they also add a lot of gain and can provide high input impedance. Let's start with the difference amplifier, or also called the op-amp subtractor. This amplifier circuit is comprised of an op-amp and 4 resistors. If we assume all 4 resistors to be the same, This circuit has a unity gain from the voltage difference presented between V1 and V2. If the matching of these resistors is not exactly the same, then the CMRR of this circuit is reduced. What this means is that the output will not be exactly the difference at V1 and V2, but will vary with the relative position of V1 and V2, the voltage of V1 and V2 referenced to ground. A difference amplifier that has been designed to be very flexible is the AD8271. This amplifier contains different passives in an arrangement that can be used to create difference amplifiers with gains of 1/2, 1, and 2, or single-ended amplifiers with a gain of -2 to +3. Distortion is very low and very wide bandwidth for a precision amplifier. Another advantage of having an integrated passives is the very, very low drift in the gain, because all resistors track, as well as having a high CMRR due to very high matching achieved through trimming of these resistors. Some of the configurations that are possible with the AD8270 and AD8271 are shown in this slide. Another application of AD8271 is building a high-speed enamp. In this case, we're showing the ADA4627 buffering the inputs of the AD8271, but the ADA4627s are building a differential gain stage. This circuit is also known as an instrumentation amplifier. Another example of a difference amplifier application is using the AD8277. The AD8277 contains 4 resistors per amplifier, and all of those resistors have the same value. A precision absolute value circuit can be built using this product and doesn't require any diodes as a regular or the typical absolute value circuit that is shown on the top. Other applications for difference amplifiers are shown on this slide. The 4 examples here show different ways of building current sources. As I mentioned before, the generic instrumentation amplifier has 2 high input impedance inputs that can amplify a differential voltage and provide very high common mode rejection. The classical 3 op-amp instrumentation amplifier is shown on this slide. Typically, R2, R3 are the same value, and the amplifiers A1 and A2 generate the gain of the circuit. The subtractor stage only will remove the common mode voltage without adding any amplification. The resistor RG sets the gain, and in the most common instrumentation amplifiers, this resistor is external. Precision instrumentation amplifiers have this resistor internal for excellent gain drift. Instrumentation amplifiers are typically used for amplifying bridges as well as biopotentials. As seen in this example, a bridge creates a small differential signal between its 2 terminals. Because of the high source impedance of a bridge, a high input impedance is required as well as high gain. This is why an instrumentation amplifier is the perfect solution for this type of problem. As can be shown here, typical enamp applications include interfacing to sensors that are bridge-based, such as pressure, strain, temperature, vibration, and current sensing, as well as measuring biopotentials, such as EEG and ECG. Market segments include, of course, industrial, healthcare, process control, etc. While the 3 op-amp topology is the most popular instrumentation amplifier topology, there are different topologies used to build instrumentation amplifiers. There's the 2 op-amp, which has the advantage of having low cost, indirect current feedback, which is also low cost and low power, as well as current mode correction. An important parameter for instrumentation amplifiers is their input common mode range. The input common mode range indicates what is the valid input common mode voltage accepted for a given differential voltage. In other words, as we can see on the plots on the right, the amplifier needs to be inside of that plot in order to operate properly. The contour determines the valid region of operation. In this case, if we like to have a voltage at the output that is between plus and minus 10, and we have a supply of plus minus 12 as seen as on the top plot, we need to have a common mode voltage at the input that does not exceed roughly plus and minus 4 volts. Exceeding this common mode voltage would limit the swing of the output voltage, even if it hasn't reached its maximum value. Diamond plots are very useful in determining what is the valid operational range of an instrumentation amplifier. Instrumentation amplifiers, usually as they are supplied with narrower and single supply voltages, become increasingly more difficult to use due to this diamond plot limitation. The AV8237 micropower zero drift instrumentation amplifier does not have this problem. As it can be seen from this slide, the AV8237 has an input common mode voltage that exceeds its power supplies. This means that this amplifier can be used to sense or amplify voltages that are very close to ground or very close to its power supply. In this example, AV8237 is conditioning the output of a bridge, all in a single supply circuit, and feeding it into an A to D converter. A family of digitally programmable gain instrumentation amplifier is the AV825X. The difference between the different models is the different gain settings for each one. One of the advantages of using a PGIA is getting low noise, low offset with wide bandwidth, as well as high precision and good gain accuracy. For additional information on instrumentation amplifiers, we have the Designer's Guide to Instrumentation Amplifiers, 3rd edition, downloadable from our website. More resources under www.analog.com/enamps. ADC driver amplifiers have been designed to drive ADC inputs. ADC inputs usually present switching transients. An amplifier must settle after such transients and deliver high resolution and high performance. High performance ADCs also require differential input signals. This may be a problem for circuits that deal with single-ended signals because those need to be converted to differential. Differential amplifiers can take a single-ended input and convert it into a differential output that is required at the input of an ADC. The other input for the ADC is also the reference input. And for this input, another ADC driver may be required, such as an op-amp buffer. A typical unbuffered single-letter input transients are shown in this slide. You can see that the signals are being affected by the switching transients, and these transients match the edges of the sampling clock. The AD8475 is a differential funnel amplifier and ADC driver. The advantage of this amplifier is that it can take the regular and most common plus and minus 10 volts single-ended signals and convert them into a differential signal that can fit into the input range of a modern ADC. In this example, included in the circuit note CN0180, shows the AD8475 conditioning the signal plus minus 10 volts for the inputs of the AD7982, which is a high-performance 18-bit SAR ADC, and it can sample up to 4 megasamples per second. Another example of an ADC driver for wider bandwidth signals includes the ADA4932. In this case is shown driving the input of a 16-bit 10 megasamples per second ADC, the AD7626. An example of an ultra-high precision, low noise voltage reference is the AVR45XX family. The different model numbers include different voltage outputs. This is an ultra-high accuracy with a voltage drift of 2 ppm per degree C, excellent noise performance, and a wide temperature range operation. Current sensing is another difficult function. Benefits of precision current sensing done with integrated amplifiers include lower cost, improved diagnostic capabilities, precise current sensing, and improved system efficiency. Current sensing is used in many control applications. In this case, I am showing some automotive applications, such as automatic transmission, diesel injection, electric power steering, and electric motors. In general, high side current sensing allows for lower cost, improved diagnostic capabilities, improved current sensing, and improved system efficiencies. In this slide, I am showing an example of a low side current sensing. You can see that while this requires a low cost amplifier, it requires higher cost switches, higher cost drive for that switch, and short circuit current does not flow through the shunt, which does not allow for diagnostics. In this case, high current sensing requires lower cost switch and low cost drive, which makes for a lower cost system and also allows diagnostic and protection for shorts to ground. The trade-off is that it requires the use of a differential amplifier with a high common mode range. Current sense amplifiers can meet these requirements. Their typical applications are DC to DC converters, power supply monitoring, solar panel monitoring, motor control, valve and solenoid control, as well as power amplifiers. The AD8210 is a current sense amplifier, and it's shown in this slide performing two functions: DC motor control and DC to DC conversion. In both cases, the shunt is sensing the current going into the load, in this case a motor or a static load, but its common mode is changing constantly. The AD8210 can reject this quick common mode voltage changes, reducing the spikes at the output. For high common mode current sensing, we have the AD629 and the AD8479. These two differential amplifiers can take up to 270 and 600 volts of common mode voltage with supplies of plus minus 15. In this example, I am showing the current monitor with a 500 volt common mode voltage range. In this case, the amplifier is the AD8212, and this amplifier can float to very high voltages. The circuit note CN0218 shows more details on the circuit. Several tools are available in our website to help you with your design. On this slide, I'm showing ADI Sim Op-Amp, which is very useful when designing op-amp circuits. It can help with the amplifier selection as well as with resistor values. The ADI DFAM calculator is also available for download. It can help with the proper differential amplifier selection as well as selecting proper resistor values for operation. We also have the ADI version of Multisim Spice downloadable from our website. This is free of charge and includes already a library of ADI standard models. In summary, we have covered that op-amps are very versatile devices that can be set up for many applications. Op-amps cannot amplify an input signal with a higher gain than their own noise, so we have to pick low noise op-amps. But we also have to consider the dominant noise source. Specialty amplifiers are built-up combinations of op-amps that are specifically tailored for complex applications. High-performance ADCs require high-performance driver amplifiers to obtain full accuracy. Differential amplifiers can pick small signals from very high common mode voltages. Also, new software and online design tools can greatly simplify product selection and system design. Some of the design's resources covered in this session include the ADI Sim Op-Amp, DFAM Calculator, and Multisim Spice. You can also ask technical questions and exchange ideas online in our Engineers Zone support community at ez.analog.com. You can also access the design conference community under www.analog.com/DC13community. I'd like to remind you to visit the current monitor with 500 volt common mode voltage demo in our exhibition room. This circuit features 500 volts of common mode with 0.2% accuracy. The circuit benefits include minimum loading and fast response. The circuit shows AD8212 floating on a large common mode voltage and taking a current sense measurement that is then digitized and passed through an isolator. You can also visit the weight scale demo in the exhibition room, which measure weights from 0.1 grams up to 2 kilograms. This demo also uses the SDP board. This demo board is also available for purchase from www.analog.com/DC13-hardware.